Hello everybody, welcome to our content in group theory for week 4. So our goal this week is to talk about Lagrange's theorem, which is really one of the most important theorems in finite group theory. What it says is that if you have a subgroup of a finite group, then the order of the subgroup must be a divisor of the order of the group itself. So for example, Lagrange's theorem says that there's no point in looking for a subgroup of order 16 in a group of order 24, because there can't be one. 16 is not a divisor of 24. There's no point in looking for a subgroup of order 7 in a group of order 30, because 7 is not a divisor of 30. So that's Lagrange's theorem, and it's a really important piece of sort of structural information about finite groups. It tells us the potential orders of subgroups of finite groups if we know the order of the whole group itself. So let me just recall a couple of items of terminology. The order of a group is the number of elements in it. If the group is finite, an infinite group is said to have infinite order, and Lagrange's theorem doesn't say anything about infinite groups. It's a theorem about finite groups. So it tells us what the potential orders of subgroups of finite groups are in terms of the order of the group itself. Okay, so just a couple of remarks here about the words that appear in this slide. So first of all, divides. The word divides that appears there, remember the word divides means is a factor of. So it's not the same use of the verb divide as when you talk about dividing one number by another. To say that 3 divides 21 is the statement that 3 is a factor of 21. Okay, so we can read this symbol as 3 divides 21. The symbol for divides is a vertical bar. And actually, let me just mention that's something that's often confused with backslashes and forward slashes and other symbols that are used in fractions, for instance. The symbol is a vertical bar. It's not a hyphen or a forward slash or a backslash. It's a vertical bar, and it's the shorthand that's used for the term divides. Okay, so Lagrange's theorem, for example, says that a subgroup of S4, the group of all permutations of 4 objects, can possibly have 1, 2, 3, 4, 6, 8, 12, or 24 elements in it, because these are the positive integer divisors of 24. So for example, a subgroup of S4, since S4 has order 24, which is 4 factorial, couldn't have 7 elements, it couldn't have 16 elements. Lagrange's theorem also says, of course, that a proper subgroup of a finite group cannot contain more than half of the elements in the group. If it contains more than half of the elements, it has to contain all of them. So remark, the converse of Lagrange's theorem is not true. Lagrange's theorem does not tell us that S4 or any other group of order 24 has subgroups of all of these orders. It tells us that the only subgroups it could have must be of orders from those lists. So it's not true that every subgroup of order n has subgroups of all orders that are divisors of n. There are counterexamples to that, and that in itself is quite an interesting topic. Okay, so Lagrange's theorem says this very sort of major thing about subgroups of finite groups. We're going to prove it. That's our goal for this week. We're not going to do it all in one go. It's a reasonably, it's a major theorem. It takes a little bit of machinery to prove it, but not an awful lot, and nothing that's out of our reach. Just a comment about it, I think, is that this is quite a remarkable thing, this theorem. And what's even more remarkable, in my opinion, is the fact that we can prove it with nothing but the axioms of a group. And that's what we're going to do shortly, using some concepts that we already know, and one more that we're going to introduce. So, in my opinion, this is a kind of a really good sort of advertisement for the power of the abstract approach to algebra, and the axiomatic approach to algebra, whereby you've got some axioms, that's all you have. This theorem is saying no matter what our group is, no matter what its elements are, no matter what its operations are, as long as it satisfies the basic axioms of a group, we're going to be able to prove that it has this property, that the order of any subgroup must be a divisor of the order of the group itself. It's certainly not an obvious fact, and far from obvious how we're going to go about trying to prove this theorem in a completely abstract context where we have got no idea what our group G is or what its subgroup H is. All we have recourse to are the axioms of a group, but that's what we're going to do. In order to do it, so let me just say how this will go. So this is the first of our 2 video lectures this week. This one is going to explain sort of the mechanism of the proof of Lagrange's theorem that we're going to be able to complete. And it's also going to introduce one key concept, which is something called a coset. And the second video, which is really part 2 of the same thing, will prove a key property about cosets that we need to prove the theorem of Lagrange. So really, the first video here will have all of the ingredients of the proof and hopefully reasonably accessible explanation of this proof, except for one technical property about cosets, which will appear in the second video. None of it is complicated. All any of it uses is the basic group axioms, but because of the abstract context, it can take a little bit of thinking about to get used to it. Okay, so here's the key concept that we need. So supposing we're in the situation of the theorem of Lagrange, where we have a group G, its binary operation, we call it star. And G has a subgroup H. At this stage, we don't care whether G is finite or infinite. We will care when we're dealing with the Grandest theorem that it's finite, but for now it can be either finite or infinite. Okay, so we've got a group G with a subgroup H. Remember what that means? G is some big group. H is a subset of G that is itself a subgroup under the operation of G. We're going to give ourselves an element X of the group G as well. Okay, then the left coset of H in G, determined by the element X, which is denoted by X star H or just XH, is a particular subset of G. And what it is the set of all elements that you can get by taking an element of H and composing it on the left with X. Okay, so the setup is we've got a group G, we've got a particular subgroup H in mind, we've got a particular element X in mind as well. And the left coset of H determined by the element X is a set of all elements of the group that can be obtained by taking an element of H and composing it on the left with X using the operation in the group. We'll look at a couple of examples in a minute, but first of all, a couple of comments. So it's a technical definition. Not obvious at first glance, I think, why it's interesting or why it might be useful, but hopefully we can at least sort of see what it says. You know, if you have a particular subgroup H in mind and a particular element X, this is how the left coset of H determined by X is defined. Why we would care about it is yet to be revealed. Okay, so our way of thinking about it though is, you know, we've got the subgroup H living inside G. We're going to hit all the elements of H on the left with this fixed chosen element X. So we're sort of translating them away from the subgroup H itself to some other subset of the group. So we can think of this coset as being sort of like a shifted copy of H inside the group G. Okay, the coset is a subset of G, generally not a subgroup. We don't expect it to have its own algebraic structure. We don't expect it, for example, to be closed under the group operation, but it's a subset of the group G. Okay, third remark, it's possible for two different elements, X and Y of G, to determine the same left coset. Okay, so every element of G determines a left coset of H, but it's not necessarily true that different elements determine different left cosets. And to see that, you know, think about the example, for instance, where X itself happens to be an element of the subgroup H. In that case, X star H will always be an H for every element of H because H is closed under the group operation star. So in that case, if X is an element of H itself, this left coset that is determined will just be the subgroup H itself. Okay, so two elements will determine the same left coset, for example, if they both actually belong to the subgroup H itself. Okay, fourth remark, there's a corresponding concept of right coset. We're sort of privileging the left here by choosing to define left cosets instead of right ones. It doesn't really matter, you could do it for right cosets instead. There's no big reason to prefer left ones. We will be interested in right cosets later, but not just yet. Of course they exist and you can define them in exactly the same way. Okay, that's what a left coset is. It's a new concept for us. It's one that's going to be really important, not only in group theory actually, but also in other fields. So although the language can differ a little bit from field to field. So just to kind of make sure that we have a clear understanding of what it means, let's look at a few examples, some that we're already probably familiar with, and one or two that we might meet now for the first time. Okay, so if we give ourselves the group of integers under addition, and just for consistency with the notation of the definition on the last slide, let's call it G, even though typically we call it Z with a plus for addition. So if G is the group of integers under addition, and H is a subgroup consisting of all multiples of 5, so 5, 10, 15, 0, minus 5, minus 10, that's a subgroup of the integers under addition. Okay, then according to the definition, the left coset of H in G determined by the integer 3, so 3 here has the role of X in our definition. The multiples of 5, 5Z, have the role of H, and the full group of integers under addition has the role of G. Okay, the left coset of H in G, determined by the element 3, is the thing that we get by taking all the elements of H, that's 0, 5, 10, minus 5, minus 10, and so on, and adding 3 to all of them. So instead of 0, 5, 10, we get 3 plus 0, 3 plus 5, 3 plus 10, 3 plus minus 5, and so on. So we get the subset of the integers whose elements are minus 2, 3, 8, 13, and so on. They differ by 5 from one to the next. Okay, so that's what the coset determined by 3 is for this particular subgroup of the integers according to the definitions on the last slide. And of course, we might recognize it as something else that we're familiar with. It's the congruent class of 3 modulo 5. It's a set of all integers that differ from 3 by a multiple of 5. Okay. So we can think of it as taking the multiples of 5 spread along the number line, which is just a set of like integers spaced 5 apart. Just taking that entire set and moving it 3 steps to the right by adding 3 to everything that's in there. And then we get another set of integers, again, spaced apart by 5, but this time instead of 0, 5, 10, it's 3, 8, 13, and so on. So this is the congruence class of 3 modulo 5. In the language of group theory, it's a coset of the subgroup 5z, represented by 3, or by 8, or by -2, or whatever. So all of those elements determine the same coset. They're all congruent to each other modulo 5. Okay? And the different cosets of 5z and z determined by different elements are just the congruence classes modulo 5. So this is an example that we're already familiar with from studying modular arithmetic. And maybe it's a good one for kind of reinforcing the concept of what a coset means. And it's not actually not relevant to the Grandest theorem because it's in the context of infinite groups rather than finite, but it does capture the concept of coset. A second example, suppose we take the group GL2Q, the general linear group of all 2 by 2 rational matrices under matrix multiplication. And suppose we take H to be the subgroup SL2Q. This is called the special linear group, which consists of all the matrices of determinant 1. So G has all the 2 by 2 matrices of rational entries and non-zero determinant. H has only those ones which have determinant 1, and H is certainly a subgroup of G in that situation. It's called the special linear group. The left coset of H in G, determined by this particular example of an element of GL2Q. So this is certainly a matrix with rational entries and non-zero determinant. Okay, by definition of coset, the left coset of H in G, determined by that matrix, is the subset of GL2Q, consisting of all matrices that you can get by taking something that's in SL2Q, taking something that's in H, so taking something whose determinant is 1, and multiplying it on the left by this matrix using matrix multiplication. Okay? And we can figure out what that is as a subset of the entire general linear group. If we take something whose determinant is 1 and multiply it on the left by this invertible matrix, the determinant of that product is going to be the determinant of this one times 1, which is going to be -6. The determinant here is 6 minus 12, so it's -6. So in fact, every element of this subset has determinant -6. Not only that, but every matrix of determinant -6, whose entries are rational, is in this set because it can be obtained by multiplying something of determinant 1 by this invertible matrix on the left. So in this case, again, we can give a sort of a description of what the coset determined by a particular matrix is. It's the set of all matrices in the bigger group whose determinant is the same as the determinant of this one, which for this example happens to be -6. That's one remark. The second remark is that we can observe that for any other example of a matrix in GL2Q whose determinant was -6, if we did the same trick for that one, we would get the same coset as the result. So all matrices with the same determinant give us the same left coset in this particular example. Okay, in this case, the one that we chose to be our representative has determinant -6, and the coset is the set of all matrices whose determinant is -6 in GL2Q. Okay, so that's another infinite example, but it's another example where you can kind of give a meaning to what these cosets are. The cosets are just all the subsets of GL2Q on which the determinant is constant. The subgroup itself is the ones with determinant 1. The coset determined by this one is all the matrices with determinant -6, and so on for other examples. So that's another one. Third example. This is kind of relevant to the Grandest theorem. So if you're working on the current homework sheet and you're writing out the multiplication table for the group D8 of symmetries of the square, this might be of interest. So if G is the dihedral group D8 consisting of all symmetries of the square, and H is a subgroup of G consisting of the 4 rotations, then we can ask about the left coset of H and G determined by any one of the 8 elements of G. Okay, if we choose one of the 4 reflections to be our chosen element, then what we're doing is we're composing that reflection with each of the 4 rotations in turn, and the set of 4 elements resulting from that is the coset determined by that reflection. And in all cases, regardless of which reflection we choose, the result of that would be the set of the 4 reflections. If the element we choose is one of the 4 rotations, and we compose it in turn with each of the 4 rotations, what we get are the 4 rotations again. So in this instance, there are only 2 distinct left cosets, one consisting of the 4 rotations, determined by any one of the 4 elements that are rotations, the other one consisting of the 4 reflections, determined by any one of the elements that is a reflection. So it's quite a nice example, and in fact this one exactly captures how we're going to prove the Grandest theorem. What we find is that we have 8 elements, each of them determines a left coset, but there are only 2 distinct left cosets, because all the 4 rotations determine the same left coset, that consists of the 4 rotations, all the 4 reflections determine the same left coset, that consists of the 4 reflections. I'm not saying that this is completely obvious, but it can be read off from the group table for D8. So we find there are only two distinct cosets. Each of them has 4 elements, which is the order of the subgroup H. And the two of them together make up the whole group, and they're disjoint. There's nothing in their intersection. And this is in general what we're going to discover, that a finite group, if it has a subgroup, will be a union of disjoint left cosets of that subgroup determined by different elements. Each of those left cosets is going to have the same number of elements as the subgroup itself. And by adding up the numbers of elements in all of them, which are all separate and disjoint from each other, we'll get the total group order. So it will have to be a multiple of the order of the subgroup. This example hopefully might show, might give an inkling of how the theorem actually works. There's something that we have to prove, of course. We have to prove some of these properties of left cosets that I'm claiming. We can check it easily for the example of G8. But the assertion is that if you take 2 left cosets of any subgroup in any group that are different from each other, that are not the same set, then they won't actually intersect each other at all. So basically the group sort of falls apart into a collection of separate cosets, all of which have the same number of elements as the subgroup itself. And when you add up that number of elements the right number of times, you get the entire group order, which is how we justify the assertion in the theorem that the order of the subgroup must be a divisor of the order of the group. So what we'll do next is just have a look at the mechanism of the proof, which is basically what I just said. Hopefully maybe this example might be helpful as a reference point there. And then in the next short lecture, we will come back and prove some of the properties of cosets that are asserted here and that we would need to prove in order to complete a proof of the theorem of Lagrange. But the mechanism for Lagrange's theorem is basically the following. So we're in the context of Lagrange's theorem. We have a finite group G. It has a subgroup H. If you find that just too sort of abstract, that completely in that context, feel free to kind of specialize to an example like the one of the last slide with the dihedral group of order 8. But that's the setup. We have a finite group G. It has a subgroup H. Okay, what we're trying to prove is that the number of elements in H must divide the number of elements in G. G is finite, so it has a number of elements. Okay, so first possible case that could happen, if H is actually all of G, then certainly the theorem holds because the order of H and the order of G are the same number, they divide each other. Okay, so that's fine, that's kind of the easy case and it's not really saying anything. But if H is not G, then so here's a picture. So the whole rectangle here is supposed to represent the entire group G. And somehow kind of down at the bottom of it, we have this little slice, which is the subgroup H. Okay, so in here, in subgroup H, we have some elements. It's a very nice thing because it has algebraic structure. It's closed under the group operation. It has the identity element in there. It has inverses for all of its own elements and so on. Okay, but if the subgroup H is not all of G, that means that there's some element of G that isn't in H. Okay. And if we look at the left coset generated by that element, the assertion is that that left coset, it's certainly not the same as H because it includes the element X, which isn't in H. But the claim is, and this is what still has to be proved in the next installment, that coset XH is disjoint from H. It has no elements in common with H. And the number of elements that it has is the order of H. That part is sort of relatively easy to see because the elements of this left coset are just found by taking all the elements of H and composing each one on the left with the element X. And that certainly, will leave us with the same number of elements that we started with. It won't, for example, force any of them to become the same if they weren't the same before, or anything like that. So what happens then in the picture is we've got this next slice, which is XH, the coset determined by that element X. Okay, now, if the union of H and XH is the entire group G, that's a possibility, that's fine. If that happens, we're saying that the entire group G consists of 2 pieces, each of which has the same number of elements in H. And in that case, the number of elements in G is just twice the number in H. So again, Lagrange's theorem is satisfied. If the union of these 2 pieces is not all of H, it's not all of G, then there's another element Y, which isn't in H and isn't in XH, but it's outside of both of those cosets. In that case, the assertion is that if we throw in the coset determined by Y into the mix, that will again consist of the same number of elements that we have in H, but there'll be a different collection of elements that has no intersection at all with the elements of H or the elements of XH. So it's another slice, another chunk of the group G that has the same number of elements as the subgroup H. Okay, and again, if that's all, if we have all the group at this stage, what we're saying then is that the order of G is 3 times the order of H. If we don't, we take another slice and another one and so on. And eventually we have to fill up the whole group because the group only has a finite number of elements and every element belongs to some coset. So eventually, after k steps maybe, we reach the last one that completes the group. And what we have done then is kind of slice the group up into a bunch of pieces, each of which have the same number of elements as the subgroup H and which are disjoint from each other. So we can conclude that the number of elements in G is the number in H, plus the number in H again, plus the number in H again, and so on, up to until we complete the entire group. So it's K times H for some positive integer K, which incidentally is called the index of the subgroup H in the group G. Okay, so what we have to still prove in order to sort of assert that we've completed the proof is some of these concepts, some of these properties that we've claimed about cosets, namely that if you take an element X that isn't in H, then the coset that it determines is not going to intersect H. That if you take an element Y that's not in the coset determined by X and not in H itself, that the coset it generates, that it determines, would be disjoint from both of those two. So there's something to prove there, which will rely upon the whole machinery of what it means for G and H to be groups. But I will come to that in the next one. I suppose the point really so far is to familiarize ourselves with what Lagrange's theorem says, to kind of get used to the concept of a left coset, which is really worth spending a little bit of time on, and we'll reward a bit of reflection on it. Hopefully those examples might be of some use, and hopefully to understand the mechanism of this proof, and details will be filled in the final installment. Okay, that brings us to our first challenge for this week, which relates to the Euclidean plane, something that is very familiar to all of us, but even not in the context of group theory. So the Euclidean plane, the usual coordinate plane, is a group under addition of vectors. It's also a vector space, which means that its elements, as well as being added together, can be multiplied by real numbers. So your challenge is, first of all, to figure out what are the non-trivial proper subgroups of the Euclidean plane that are also closed under multiplication by real numbers. Okay, so non-trivial means containing more than just the identity element. Proper means not the entire group or to itself. And then the second part of it is, for such a subgroup, what do its left cosets look like? The left cosets of that subgroup determined by different elements of R2. So there are many of these non-trivial proper subgroups of this type. They all look alike geometrically. So really your task is to figure out a geometric description of what these subgroups are and what their cosets look like. Okay, thank you very much, everybody.